All right, insulin in the fed state. This comes from another book. So you eat a meal, and now you notice all the controllers for insulin. All right, your gut stretches. Sensory neurons, central nervous system, parasympathetic system, vagus nerve causes the beta cells to put out insulin. The carbs get to the small intestine. 2 hormones are released that cause the beta cell to put out insulin. You've absorbed the amino acids and the glucose. The rise in those blood levels cause the beta cells to put out insulin. So notice all the multiple controls. These two, these are, you might call it feed forward. Blood glucose hasn't risen yet, but you've eaten, so it will. So they start putting out insulin in advance of glucose starting to rise. And then, of course, once glucose and amino acids rise, then insulin is released. Then insulin, again, is going to put those GLUT4 transporters into the cell membranes, muscle, adipose, other cells of the body. Glucose is going to move in. The liver is going to start storing that glucose into glycogen, into fats, into proteins, going to start building, if you remember this is heavy on chapter 5, start building products. That drop in blood glucose, the digestion of the carbs, the stomach going down in size, that all decreases insulin production. And then that's going to be our negative feedback. Okay, questions about that? All right, let's talk about glucagon. Glucagon is the opposite of insulin. Its job is to keep glucose levels high to protect the brain. Now high, I mean high enough for the brain. 50% of the glucose in the body is used by the brain as glucose. So the brain is very greedy about its metabolic needs, cannot handle any drop in glucose below normal. So glucagon's job is to keep the glucose levels up in between meals. And its job will be to do whatever it has to keep the glucose level up. So that's breaking down, promoting the liver to break down glycogen to release glucose. It's going to be a primary one. We're not going to let glucose go into the organs because the organ that needs it is the brain. And there's the pathway for glucagon. Okay. And of course it's doing gluconeogenesis. We know all that stuff. We're going to start breaking down fats. And then here it is in a figure showing that during the fasting state, we're going to be using our stores of energy, glycogen, fat, protein, to keep the organs going. And there's the feedback for glucagon. So glucose drops, and that causes the beta cells to be inhibited, but activates the alpha cells to put out glucagon so we can start increasing blood glucose. And that will be our negative feedback. Now there are some who say that glucagon actually stays pretty constant. You notice that despite the meals and in between the meals, there's just a little bit of rise with our evening meal, but otherwise glucagon stays pretty constant. Insulin, however, goes up and down as we eat to keep our glucose levels within normal limits. Recall sympathetic, parasympathetic. Sympathetic turns off insulin, turns on glucagon. Parasympathetic turns off glucagon, turns on insulin. Notice that one. Talk more about the stress, the effects of stress. That the sympathetic is going to increase blood glucose by inhibiting insulin. So if you encounter patients who are in the immediate trauma state, they've just had the car accidents, for example, they've just had the big heart attack, the sudden cardiac arrest, you've revived them, they will have a higher than normal glucose. It doesn't mean that they're diabetic. It means that they're stressed, that the sympathetic system is engaged. But if it is a diabetic, oh, exactly. Now Kim went. If this is a diabetic, then their blood glucose is going to skyrocket. And then I told you about these two hormones, duodenum and ileum, that they are the ones that are being secreted to get insulin to come out. And then basically, again, Insulin and glucagon are alternating to keep blood glucose at a normal level. Okay, questions about that? Because now we talk about what happens when it goes wrong.
Is there a disease or is there something that people can't produce glucagon? Is that?
You don't ever hear about that one. That's a good question. No one's ever asked me that, nor have I ever been aware of one.
Okay.
Because you're going to have to continuously eat,
Yeah.
including during the night.
Well, I was just wondering that insulin comes from the beta cells.
Mhm.
Is there anything that
Google.
attacks the alpha
stand it.
cells and then no more glucagon?
Deficiency disease. Oh, she had multiple organ deficiencies, this particular person. The alpha cell deficiency was part of polyglandular failure syndrome. So, yep.
Yeah.
Okay. Pancreas endocrine tumors. Okay, come on, let's go.
So they would basically have to be put on like an IV.
Yeah, just about.
Oh, like an insulin pump.
Except glucose. Yeah. And look, the tumor, glucagonoma.
Glucagon, no more.
Yes.
No more glucagon.
Okay, there's glucagon deficiency. It's been researched against a number of hormones, deficiency linked to. Oh, okay. Well, good
Okay,
question.
thank you.
Okay, other questions? All right, diabetes mellitus. Let's talk about the origin of the word. Diabetes means flow of fluid through a tube. The diabetic, both diabetes mellitus and diabetes insipidus, are peeing a lot. They're producing large quantities of urine, so lots of urine through a tube. Mellitus means sweet, insipidus means bland. So yes, the early medical students had to taste the urine.
Mm-hmm.
They're peeing tons. Why are they peeing? Is it because they have diabetes mellitus? Sweet urine? Somebody's got to taste it, and it was the medical students who had to do it. Or probably poor Charles Best. It's a good thing they got some money. And then diabetes insipidus is a disease of the posterior pituitary, in which you put out tons of urine because you don't produce ADH. And that urine has no taste to it. It's bland, like pure water. But again, you're going to have to taste it to know. Now, back in my day, it was called juvenile onset and adult onset. What happened in our society? Kids got fat. Exactly. So now it's called type 1 or insulin dependent and type 2 insulin independent. And the shift is now, it used to be 10 and 90. So now, of course, we have more type 2 diabetics because of obesity. The Choctaw Nation diabetes educator has clients who are as young as 8 who have type 2 diabetes. And I think, did not talk about this in this class, I read about somebody who was 3 who had type 2 diabetes. There's a 3-year-old who weighed well over 100 pounds, like 150, something like that. A 3-year-old, come on. I know.
I think I saw that on like Maury one time or something.
Yeah, and that child had type 2 diabetes. So, type 1, there's not enough insulin being put out. And I'll talk about why. I'm going to talk about this is an autoimmune disorder. The beta cells are destroyed by the immune system. We'll talk a little bit more about it in a sec here. Type 2 diabetes, they have plenty of insulin, maybe even high levels of insulin, but the insulin receptors have been removed from the plasma membrane. And because you did that endocrine worksheet, you already had part of that where you had to address the size of the adipocytes. As the visceral adipocytes stretch, receptors are removed. And we'll talk about the stereotypes to help you understand the two of them. We have some useless trivia. Mellitus comes from the Latin word meaning honey or sweet. And so the species name of the honeybee is Apis mellifera. I was just thinking about bees while I was driving because my bees have been ordered. My bees will be shipped April 16th. So in my list of things to do over the next few weeks is to get the hive set up. Get the boxes set up. All right, from your book, a comparison of the two. Notice, typically under the age of 20, though I've heard of people in their early 20s suddenly showing the signs of type 1 diabetes. This is a childhood onset. The symptoms develop rapidly, get over a few months. They will develop ketoacidosis. We'll talk about that. They are not fat. We'll talk about why they are not fat. And the beta cells are gone. There are no beta cells. So the only treatment, they have to have insulin injections. Type 2 diabetics, these are middle-aged people, comes on very slowly, and is associated with obesity because it is predominantly because of the stretch of the adipocytes. Now, stereotypically, those are going to be fat people, but not necessarily. There are type 2 diabetics who were never obese, who develop insulin resistance, but they are less common. And the type 2 diabetic can start having to get insulin injections because when they are in a severe, prolonged state, they stop producing insulin altogether. Their treatment will be diet and exercise, predominantly. We'll talk about how that works. They might get some oral tablets to get insulin production or to stop the rise in glucose in their blood. And then they might start having to have insulin injections later. But they still have plenty of insulin.
Question. Can it subside?
Yes, if they lose weight, yes. Now they're still going to have the risk of it if they ever gain weight again.
Yeah.
But yes, it will, the symptoms will decrease. And there's also gestational diabetes. Gestational diabetes, and when we talk about the reproductive system later today in the lab, the changes that the fetus is doing causes the woman's blood sugar to rise, which will cause insulin resistance to develop in susceptible women. Then they will have diabetes because they're pregnant. Those women are now more likely to develop type 2 diabetes later in postpartum. Okay, type 1 diabetics, how is it that their beta cells are killed? Killed by killer T lymphocytes. We haven't talked about the immune system yet. Typically, now they have a genetic predisposition and there needs to be an environmental factor that's going to turn it on. When we talk about the immune system later, you'll understand more. Killer T lymphocytes, their job is to kill cells that aren't right. So the cells have mutated, they have cancer, or they've been infected by a virus. So the killer T lymphocytes are activated to kill cells that have been infected by a virus, but because of genetics, it now doesn't stop there. It goes ahead and kills the beta cells.